All right, good day, students. Here we go with section 2-3 in chapter 2, which is on set theory, and we are going to look at Venn diagrams. The vocabulary is very light for this section. There's two terms, Venn diagram or Venn diagrams, which is what you're basically going to be using a lot of. And then there's another special type of diagram or thing called a partition. We'll talk more about that in just a second. So let's look at a Venn diagram. It is simply an illustration that shows a relationship between the universal set and its subsets. So let's look at an example here. So we have this white rectangle here. That would be like our universal set. And then in that universal set we could have some other set. Let's say this red circle is a set of things. Then we could have another set, this gray set, and you'll see that not only are these two sets within the universal set, they're distinct, but they do have some overlap, but they also have some parts where they don't overlap at all. So let's see if we can explain that just a little bit more. So let's say we've got another universal set here and we've got two subsets, and instead of just referring to them by their colors, let's go ahead and just give them names. So we have subset A, or we have set A, and we've got set B, which is basically the purple circle and the blue circle. And let's get even a little bit more specific with that. Let's go ahead and put some elements within those different parts of our Venn diagram. So we've got element X, Y, and there's a W, and then there's a Z. X, Y, and W, and then Z. So it says list all the elements that are in A. So hopefully my pointer is turned on here. Good. So remember, whenever we see the union symbol, we are thinking of the word or. So that means it's the things that are in A or the things that are in B. So that would be the set of W, Y, and Z. W, Y, and Z are in A or B. Alright, so let's list the elements in A complement intersect B. So let's go over what A complement is first. So A complement is the set of things that are not in A. So that would be X, which is in either one of the sets. And then we've got the element of Z. So that's what's in A complement. Now we're going to intersect that with what's in B. Now remember, whenever we see the intersection symbol, we're thinking of the keyword AND. So we're looking for, and let me just go ahead and list the things in B here. B is W, Z. So we want to intersect these two sets. So what is in A complement and in B? Well, that's simply the element of Z. Z is the only thing that's in both of those sets. Let's do one more. So let's list the elements that are in the union of A and B, and then let's complement that. So complement there. And again, well, heck, we already know what A union B is. We did that right here. That's W, Y, and Z. So what is the only thing that is not in A or in B? Well, again, it's sitting right there by itself. So the set would be X. Let's do a word problem using a Venn diagram. It says there is a group of 30 students in Mr. Allen's finite class. 19 of them are taking Mr. Potter's English class. 17 of them are taking Mrs. Mitchell's social studies class. How many of them are taking both Potter's and Mitchell's classes? Well, we could do a Venn diagram here. So I think I've already got those made. Yeah, I've got these two kind of ellipses here. They don't have to always be circles. And I'm just going to go ahead and throw a universal set here, even though we really don't need it in this particular problem. Now it says that Mr. Allen has a total of 30 students in his class. And then we'll say that this set here, let's just say that that's P for Potter. And then let's call this one over here, let's call that M for Mitchell. So let's see here, there's 19 taking Potter's class. Now here's the thing. There's a slight problem here, because if you think about it, if we've got 19 students taking Potter's class and 17 taking Mitchell's class, when you add those two numbers together, you get 36. Now that's odd, because how many total students are there in Mr. Allen's class? 30. Well, the reason that there's more numbers when you add these together than there are technically of students is because it turns out that there are 6 students in the middle. Now let me explain how I got that. Remember, I said that there were 19 students taking Potter's class. Well, there is 6 more than 30, right? There was 36 here. So 6 subtracted from 19 is 11. Now I want you to notice this. This gray circle here represents all the students that are taking Mr. Potter's class. Oh, that's not 11. That should be 13, I think. Oops. Okay, I'm screwing this up here. Forget that. Should be 13 right here, right? So there's 13 plus 6. So there's 19 total students taking Mr. Potter's class. 13 of them are only taking Potter's class. 6 of them are taking both Mr. Potter and Miss Mitchell's class. Now, there was 17 that are taking Mitchell's. 6 of them are taking Potter's as well. So that means there's 11 over here. Now let's make sure our numbers jive here. So what's 13 plus 6? Well, that's 19. Plus 11 more. So that would be 30. And that means that there is no one out here. Everyone in Mr. Allen's class is either taking Potter or Mitchell's or both. And it turns out, and the answer to our problem here is 6. There are 6 students taking both. 6 students take both. Okay? Now, I do want to point something out here. Remember, 19 plus 16 is 36. And there was only 30 students total. Why is that that number is bigger than that 30? Again, the reason is these 6 students that are taking both are actually counted twice in the total. Because there's 19 in Potter's, so if we counted them all, you'd have 13 plus 6, which is 19. Well, in Mitchell, there's 17, so 11 plus 6 is 17. But notice that I've counted these 6 twice. So, partition, our second vocabulary term and our last. A partition of P is any collection of subsets such that all of the subsets are non-empty. That means they got to have something in them. Any 2 subsets are disjoint. In other words, they have nothing in common. And the union of the subset is the entire collection of P. So we usually use kind of like non-overlapping rectangles that are, there's no space in between to represent a partition. So here we have a subset of 4 things that make up this whole partition. We'll say this whole partition is P. Notice that all of them have some space in them, so they have hopefully some elements. And then notice that none of them overlap. So visually, this is kind of what we're going for. Let's look at an example. This one's a little bit harder example than what you might find in the book because it's going to involve a little bit of algebra. You can kind of common sense your way through this, but we've got a partition and it's divided into 3 subsets. Subset A, B, and C. So I'm just going to go ahead and throw this partition picture out here. And obviously I've already created this before I did this example. And you might notice that A and B are slightly wider than C, and I'll show you why I did it that way here in just a second. It says the cardinality of the original set is 100. So the entire partition, all 3 of these things together have to be 100. The cardinality of the subset of A is equal to that of B. Notice that I try to make A about the same size of B. And the cardinality of B is twice that of C. So I tried to make B twice as big as C. Now the question here, and I should have made this a question mark, the question here is what is the cardinality of each subset? Okay, so I don't know. I mean, we could guess and check, but let's try to do it a little bit more methodical than that. Let's say that there are X things in C. Now, if there are X things in C, how many things would be in B? Well, it says that the cardinality of B is twice that of C. So if C is X, guess what B would be? It would be 2X. And then here I said that A is equal to the cardinality of B. So if B is 2X, A must be 2X. Now, I'm going to write down a definition here that's pretty important about partitions, a formula, and that is that the cardinality of subset A plus the cardinality of subset B plus the cardinality of subset C has to equal the cardinality of the universal set. In this case, the cardinality of the universal set is 100. This is one of the parts of the definition. Basically, if you add all the subsets up, you get the entire partition. So now we can just do some substitution here. So cardinality of A is 2x, cardinality of B is also 2x, cardinality of C is x. So let's see here, 2x plus x is 5x equals 100. We need to divide both sides by 5, and it turns out that x is 20. So now we can answer our question. Looks like the cardinality of C is 20, because 20 is equal to x, and the cardinality of A is equal to the cardinality of B, which is going to be 2 times x, which is 40. And you'll notice if we plug these numbers into our original problem here, 40, 40, 20, if you add those up, you do get 100. Okay, a couple of things about De Morgan's Law. We've already seen De Morgan's Law. We're seeing it here again. Basically, it's kind of the same thing that we saw earlier last month. We're just now into September. So basically, if you're going to do the complement of a union, then it becomes the intersection of their complements. And if we're going to do the complement of an intersection, that's going to be the union of their complements. So please keep a note on this one. This is handy, especially with word problems. Some other important relationships. This goes back to the example when I talked about the students in Mr. Allen's class that were also in Mitchell's and Potter's and all of that. And this is something you really just need to memorize. In general, the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of their intersection. So very quickly, to explain why that's true, if you had two subsets here, A and B, and I'm going to add these things together, let's say that's 2, that's 1, and then let's say that's 3. The cardinality of A would be 3. The cardinality of B, everything that's in B, would be 4. And then the things that they have in common is 1. So what would be the cardinality of A union B? Well, you could just count those up and see that that's 6. But if you add 3 and 4 together, you get 7. So you got to remember, you got to subtract that 1. The reason it's true is you end up counting that 1 twice. The cardinality of the complement of a subset is basically the cardinality of the universal set minus the cardinality of A. And the cardinality of a Cartesian product is simply the product of each of the individual sets. So if I had a subset A that was, let's say A was the set of 1 and 2, and the subset B was the set of 2, 3, and 4, and you start cross-producting those, you'll have 2 things times 3 things, so you're going to get a total of 6 things. So here are some practice problems. I'm going to go through them, and then you can check my website for the answers. Problem 1 is this. I would like you to find the cardinality of the union of those sets, A and B. Draw a Venn diagram, or use the formula. Problem 2. In a survey of 1,000 students, 423 of them reported watching channel 13, 319 channel 6, 89 viewed both. How many only viewed one of these channels? How many viewed neither? So there's a couple of questions in this one. Problem 3, this is a big one, so you're going to have to pause this one probably a couple of times. 120 consumers, and we've got 3 markets that have, or 3 different labels. And I'm going to show you the results here on this page. So we've got 12 at A and 25 on down the line. Pause that. So now here's the question. How many are sold under at least one of the 3 labels? How about label A or B but not C? How about label A? How about none of them? Again, the answers will be posted on my website. Have a good day.